So we've been hearing about client, we've been hearing about cloud and network, and we've heard it peppered about the discussions is security, okay? And I'm really pleased that you're able to join us today. Dennis Mattoon, he's Principal Software Development Engineer at Microsoft Research. And you're also co-chair for the Marketing Workgroup for the Trusted Computing Group. So Dennis, I'm going to let you take it away. You just have to share your screen.
Yep. All right. Thank you for that, by the way. Can you see the slides I'm sharing?
Yes, I see it. You're good to go.
Good. All right, well, thank you, Neil. As I said, my name is Dennis Mattoon. I'm with Microsoft Research. I've been there about 15 years now. And also speaking in the context of TIFCA here on behalf of the Trusted Computing Group as well. So let's get started. There'll be a brief introduction, talk a little bit about the intersection of these two organizations and why it matters, and how security, and of course, why security plays such an important role in remote work and play these days, now more than ever. It's always hard to gauge the level of depth based on, as a function of time for these kind of presentations. So I'll try to keep it quick and snappy and interesting. Talk a little bit about hardware roots of trust, what they are, why they're important, and an example of one, which will sort of help us understand how these things work a little bit. And so I'll just get started and we'll get there. So as I said, part of Microsoft Research. Broadly, our research agenda includes security, privacy, and cryptography. And my team in particular has been focused on hardware security for the better part of maybe 10 years now. And that's all kinds of hardware security, everything from IoT to the data center, from little industrial sensors all the way up to critical infrastructure to cyber physical systems, where the safety of humans is a concern. And I'll post it here. You see the most recent stuff we've been responsible for on the team. The TPM, I'm sure lots of you have heard of these, the Trusted Platform Module. My team is responsible for the TPM 2.0 specification. Guy on our team held the pen, Dave Wooten. We're responsible for building the reference implementation for the TPM, partner enablement, the tools, the platforms, the test suites, all that stuff. And during development of the TPM, we start to realize that, yeah, TPMs are great. They're in PCs and every workstation now, laptops, the data center. Except when you think about the explosion in the number of connected devices, whether it's for work or play or across any vertical you can name, there's just billions of internet connected devices and more all the time. So you can't always afford, either in terms of BOM cost, the bill of materials cost for the part, or intellectual debt, or for whatever reason, including a TPM is infeasible. But at the same time, we realized there are some incredibly powerful security scenarios and capabilities that you can build on a TPM. But how do we address those same concerns on the billions of IoT devices out there? So our project in MSR, originally called Riot, but for obvious reasons and for trademark reasons, we couldn't bring that code name into the public sphere. When we did bring this and contribute this back to the Trusted Computing Group in TCG, it's now referred to as DICE, the DICE Device Identifier Composition Engine. So you can think of that as the TPM is a big beefy security module in PCs and workstations in very traditional computing environments. And for everything else, we have this Riot, this DICE hardware root of trust, and we'll talk about what that means and why it's important. The other aspect of this, and I'm sure you guys are familiar with zero trust principles or trusted computing principles, whichever camp you originally come from. We'll talk a little bit about the terminology there too. We have to have this assume breach mentality, right? It's great to think defensively. It's great to think we're doing all the right things to make sure our devices are protected, but you must assume that someday something in your control will be owned. So you need a story for that, right? So we can defend all we want, except we also need mechanisms to detect a breach and to recover from that breach as quickly and as automatically as we can. So sort of an offshoot of CIRES, the Cyber Resilient Technology Initiative. It has the added value of not only recovering from when breaches do occur, but reducing the need for human interaction to recover from these different things. And I mean, that's a whole other talk. So maybe one day. So whether or not you've heard of these three sort of pillars of our work, you have no doubt heard of the various things that leverage these technologies that are out in the field. So Azure hardware has requirements for TPMs and DICE. Every Azure component that enters the data center has to have this hardware root of trust technology. Xbox, on every Xbox out in the wild, there's this thing called the HSP, the hardware security processor, that leverages these principles. Pluton is essentially a little SOC that implements a TPM, which also uses DICE as the hardware root of trust to sort of anchor the trust in the TPM, which we'll cover that too. Of course, BitLocker data at rest protection that's built on the TPM, and Microsoft has their new favorite thing in security is to add something guard, right? Device guard, credential guard, these different things. Wherever you see that guard sort of keyword, that's built on either, of course, they all involve the TPM, but also either some sort of virtualization based technology as well. So the sort of connection between leveraging hypervisor technology alongside these roots of trust principles in order to dynamically reset our trust chain. And we'll talk a little bit about that in a second too. Oh no, I lost my place in the notes. So these efforts are great because we're finding ourselves in an increasingly distributed and remote work and play environment. And we have, because of this explosion in devices and requirements and demands, proprietary solutions, of course, we've known for a long time that proprietary solutions, especially in the realm of security, aren't a great idea. But now more than ever, we're starting to see in practice people start to retire those proprietary solutions in favor of more open standards, and that's where TCG comes in. So TCG is a not-for-profit global industry standards group. Their goal is to produce vendor-neutral open standards and specifications to enable secure computing. So big picture, Microsoft Microsoft Research, my organization anyway specifically, and TCG share that goal. And at TCG, there's lots of different technology and platform work groups that are working on these different kinds of things. And then there's marketing. So you met Thorsten earlier, me and Thorsten co-chair the marketing work group, and that's where sort of the messaging of these kind of things kind of gets out. So a little bit on that sort of shared goal. So broadly, TCG and Microsoft have that same shared goal of enabling secure computing. And the reality of this new working from home, not exactly phenomenon, it's kind of sort of happened for a long time, but in the last couple of years, obviously it's kicked off more than ever, and it's not really going to change anytime soon. We're not going back. The reality is the new security perimeter for your corporate IT, for your corporate network or your IT environment or wherever is now the home office. And these days, bring your own device policies are becoming the norm, which again, even more of a reason why we want to leverage open standards, because lots of different devices, your IT environment, your IT manager can't necessarily predict or even issue you a device with particular stuff on it. So let's see here. And again, I hesitate to include a statistics slide because everybody includes statistics slide. There's a million of them out there. You're already aware of all of them. Pick your favorite. This is all going in one direction. So how is it that we keep these things secure? There's lots of different sort of scenarios out there. And enabling secure computing, that sounds like a pretty broad goal, right? But when you break down this problem, you discover that all these seemingly very different use cases, from protecting sensor networks and gas pipelines all the way down to making sure you're the only one that can access your video doorbell. I mean, these things all have the same high-level requirements. They have the same sort of fundamental elements. These devices need to be able to protect secrets. You need to be able to make sure that the devices are able to protect themselves, keys, credentials, these kinds of things. We need to also be able to make sure that when your network or the CSP or whomever is talking to your device, we have to have some assurance that you are who you say you are. So we have to have some mechanism to reason about the hardware, firmware, software, et cetera, on the device. And none of this is worth anything if we can't communicate securely, if we can't authenticate the device, if when you need that data, it's not available. So these are sort of the three main, things that the hardware root of trust is tasked with ensuring. So the simple definition of a hardware root of trust as put forward by TCG, and again, lots of different definitions for a root of trust, but you'll notice if you look at a bunch, you'll see the same sort of central elements. The root of trust is a component that performs one or more security specific functions like measurement, storage, reporting, verification, these things, sometimes update, often recovery is another one that's not mentioned here. It's trusted to always behave in the expected manner because this misbehavior cannot be detected under normal operation. What that really means in sort of plain English is it's the lowest level thing. I don't have the ability to reason about it. And so I have no choice but to trust it. And in this context, trust doesn't always mean, actually, it doesn't mean in this context that I expect this thing to always behave perfectly. It instead means I expect this to always behave exactly as I expect it to behave, right? So right or wrong, this thing is predictable. It's the same every time, and I can identify it, and that's where this, that's sort of the basis of this. So let's running over on time already. So let me go on here. And there's a little bit of terminology. We can probably skip most of this slide. Trusted computing versus zero trust. So we sometimes, especially in the marketing work group, get the question, well, geez, I hear zero trust is, the thing I'm supposed to care about, except you're called trusted computing. That seems at odds. And actually it isn't. It's just because we haven't done a good job at explaining how these are essentially overlapping concepts. So trusted computing does not mean that, hey, you're this guy, I'm going to trust you. No, of course not, even though the name would imply that. And zero trust as a term conveys better that we don't trust anything. We have to explicitly verify every single thing that happens. So, and this is the central principle for trusted computing principles as put forth by TCG. Excuse me. And embodied in the TPM and its functionality in DICE and how it operates, and we'll cover that in a second. These are the sort of the two fundamental roots of trust. So always verify explicitly, always authenticate and authorize based on all available data points. And of course, implementations will vary and your risk profile varies, how many data points and probably exactly far do I want to go with this. But we have pretty well-reasoned standards around, especially remote work in place scenarios, for exactly how far is far enough, and other very high risk, very high security scenarios can go even farther. Some examples of this out there are cryptographic based identity and attestation, essentially like device health kinds of schemes. The PCRs in a TPM or the keys and certificates produced on a DICE device. And of course, the other ones we're all familiar with. Use least privilege access, just in time, just enough access for users in any operation. Risk-based policies that are capable of adapting over time to changes in needs. And data at rest protection. Again, BitLocker is a great example, but Linux has their own versions of this too, DM Verity and other technologies that are built on the TPM and provide this kind of protection as well. And then assume breach. So defense is great, but unless you can protect secrets, unless you can recover from an issue, you're not really there yet. So organizations in this space are always moving towards more and more assurance. So what hardware support though? So okay, great. Root of trust is that lowest level thing that anchors my trust chain, that kicks off the sort of the trust in my platform overall, and that allows me to extend that trust up from the reset vector when I first power on the thing through BIOS or UEFI or the SPL, the secondary program loader in a little ARM device, or U-boot, or whatever your technology happens to be. But well, why can't I just put this in software? And for reasons you can probably guess, if a bug leads to disclosure of a device identity secret or some other kind of protected element inside the device, then how are we supposed to securely and remotely reprovision the device? And we surely can't trust software to report its own health, because in the case of an exploitable bug in some piece of your loader or your software on your device, what do you think is the first thing it's going to do? It's going to go ahead and report that, no, I'm fine. Things are great here. Don't worry about us. And it's going to just continue to function. And when these kinds of assessments are made from hardware, they come with a lot greater assurance. So inside the silicon, I can actually protect, my private key that I use to respond to challenges from my network, so that I can guarantee that when I respond to this challenge and you go and on reboot, go interrogate the identity of my device, you have a very high assurance that you're talking to the device you think you're talking to. And I, on behalf of the device, can make very authoritative statements from within that environment. And a little call out for the trust chain terminology. I'm sort of running over on time, so we'll skip that. I'll leave that as an exercise for the user. So one such hardware root of trust, DICE, the device identifier composition engine. This can be thought of as a sort of standalone root of trust for a smaller device, like an IoT device, something resource constrained, an SoC, system on a chip, or MCU. Also as a component of a component. So you have a server full of, a bunch of componentry. DICE has low enough silicon requirements and hardware requirements that those individual components inside the box can each carry this. So not only does it help in scenarios where you have little IoT devices, for example, spread all little sensors all over your industrial environment, or the network in a gas pipeline, or heart monitors in a hospital, these kinds of things. Those tiny devices, which are now targeted more than ever, can now have these significant security features that we typically associate with PCs and laptops and things like this, because in development of this DICE model, we take those essential elements that big beefier security processors have, identity, the ability to authenticate a cryptographic identity, and attestation, and we take that sort of critical functionality and enable smaller IoT devices to leverage that. And that also includes, like I said, components. So in those big beefy systems that carry a TPM, typically the original TPM, you're not really able to look into what's going on inside that little discrete part. And even worse, they can fall victim to bus interposer attacks, meaning I can sit there and snoop on the bus, tuck into the TPM, and I can go pull secrets from that. In these new models that we're seeing emerge from all the important CPU vendors, this problem has now been solved, and you'll see it coming out in architectures all over the data center, where we're using DICE as a method, as the root of trust for the TPM itself. So using it to bootstrap the communication channel with the TPM, so that we have this sort of lower level hardware root of trust that is used to enable standing up this big beefy security processor to keep leveraging those security scenarios we've all become accustomed to, but now also protecting it from all of these sort of interesting attacks that we see emerging. And of course, IoT benefits from this, because the work done to shore up these higher leverage scenarios, every device can now benefit from. So in a DICE model, we leverage the kind of thing we see in devices, a lot of devices anyway. A DICE architecture device startup is layered. So from the reset vector on, you have discrete components that form that boot chain. And beginning in the hardware with a unique device secret, you have a very well protected big random number protected in hardware. The root of trust in the hardware starts by measuring, taking a cryptographic hash of that next component that it's going to pass control to. So here you see in the diagram here, the box marked DICE, that's in ROM somewhere, that's immutable, that's in the part. And it begins by taking the measurement of layer 0, a cryptographic hash, combining that with a derivation function with the unique device secret for the platform. which has the effect of producing secret 0 you see here. And that secret is unique to the combination of this particular hardware, because that unique device secret is statistically a random number, and it uniquely identifies the hardware and is kept secret. So for example, let's just fast forward here. This as a device boots, whether it's your laptop or a tiny little sensor or your phone, this sort of measurement chain, this is a chain of trust. As it unfolds and you reach layer N, there's a secret associated with that layer N, and I'm able to go ahead and create a key, derive a key based on that secret. So when I go and talk to my service provider, I respond to the challenge and say, yep, I'm this guy's device. I do it with this cryptographic identity. And I would not be in possession of this cryptographic identity were it not for the culmination of proper measurements and derivations over the course of this chain. So when I began this process, all I had was that secret value and a bunch of software. And when I finish, I can provide a quantifiable identity that uniquely identifies this device in combination of firmware that's running on it. And you can imagine that top layer N can be something as simple as, the actual workload for a tiny sensor, or the TPM firmware, because this is a big server system and I'm only going as far as bootstrapping that bigger root of trust, or something in between, right? And this slide summarizes one of the most important features of this as well. So one of the observations you'll make is, as you're going through making these measurements, what happens if there's a successful attack, right? What if somebody manages to persist code in one of these layers? What if there's a bug that gets exploited? Well, if I've done my measurements correctly, then when layer 1 has that exploited bug and somebody managed to persist that bug on layer 1, well, my measurement came out different. So when layer 1 receives the secret, layer 1 can't and won't receive the secret that the unexploited layer 1 receives. So layer 1 will not be able to go and read the storage. If it was protected with this key, it will not be able to impersonate the device, because it can't have access to the key, because the simple fact of persisting the exploit on the device destroys my ability to obtain those keys. You can imagine also an update has the exact same effect. So let's say out in the field, I know a device was impacted, or even I have a bug on the device and I don't know if it's been impacted yet, but I want to make damn sure it doesn't get impacted. I'm going to go ahead and push an update to these devices. In advance, I can calculate, through certain methods, and go join TCG and read the specs if you want to see how. But I can predictively seal to the identity of what my update is going to yield, and know ahead of time that I'm going to drop this update on this device. When I'm done, you better be able to sign this challenge, and I'm going to expect this response, and we're good to go. And this is complicated, and we'll skip it. I think we're okay on time. Just brief DICE takeaways here. So actually, the more interesting point is the very last one. I'll skip ahead to that. You're not going to see DICE on the label anywhere. Hardware root of trust is just something we all have baked in now. This is something that's ubiquitous, whether it's in the hardware that is being provisioned into data centers today, not just Azure, but across CSPs. Whether it's in the CPU on your server system, or the IoT, the little tiny ARM device that is part of your sensor network, or the components in a satellite, the heart monitor in the hospital, the Ring video doorbell. It's in there, and it's there to protect those lowest level functions of the device that are security critical. These are the things that allow us to for example, de-emphasize legacy VPN access, as we were talking about in the last session, because now I have the TPM to protect my credentials, right? I have selective access to different areas of the network. I don't always have to have open and available my secrets, my certificate-based attestation challenges. All these different things can be protected on my device in a way that limits the ability to exploit my device, and thereby getting control of my device. And because I have a VPN, I now have full access to my corporate network. That's not how it works anymore. And I mean, maybe for some, but it's less and less true all the time. So the lessons over the last few years, which we're learning and seeing put into practice in TCG and Microsoft Research, proprietary stuff sucks. You think you can implement this algorithm better than someone else? You can't. Open standards, open solutions. More eyeballs, the better. Are what the industry is moving towards. Providers out there with proprietary solutions, those are disappearing all the time. These kinds of approaches to like defense only, no, also going away, right? We need to assume breach. We need to have an answer for recovery. And things like DICE, things like the TPM, these things provide flexible root of trust frameworks for virtually any environment with minimal silicon requirements, minimum barrier to entry. So I think I'll end here. I think I'm close on time. So I'll make that last solicitation for participation in TCG and other standards bodies. We always welcome new participants and members and you can have your say in the direction these things go.
Okay, fantastic. Thank you for joining us, Dennis.